1.2 linear functions. A linear function can be written in the form f of x equals ax plus b. You might remember it as mx plus b, but that's just a slope-intercept form of an equation, basically. One thing for it to be linear, it must have a slope. Okay, line with a slope. So example 1 says graph, tell if it's a linear function and give the domain and range. So you remember how to do this. 3/2 is the m number and 6 is the b number. So we're going to start at 6 on the y-intercept, 1, 2, 3, 4, 5, 6, and then give it a slope of 3/2, so up 1, 2, 3, and over 2. All right, that should be very familiar to you. If you're using a computer, then that's all you'll need. 2 dots is really all you need, but when you're drawing by hand, maybe you put more dots on there just so you can, I don't know, have a more accurate line. Something like that. I'm going to label that. Since we're going to have 3 different lines on the same graph, I'm going to go ahead and label it 3/2 x plus 6. That's this one. We said graph it, tell if it's a linear function, and give the domain and the range. So up above, I said in order to be linear, it must have a slope. Well, this one does have a slope. The slope is 3/2. So this is a linear function. Give the domain and the range. Well, that arrow extends on forever and ever to the left and to the right, up and down. It's going on forever and ever. Everything's going to get covered. Squash it on the x, all the x's are covered. Squash it on the y, all the y's are covered. So the domain is going to be all real numbers from negative infinity to positive infinity, and so is the range. Same thing. Part B, f of x equals 2. It might help you to think of this as y equals 2. Y equals 2. And if you wanted to think about it in slope-intercept form, I suppose you could say it's y equals 0, x plus 2, kind of like that. But a lot of people will get their y equals 2 and their x equals 5. They'll get their x's and their y's backwards. But look at where the y-axis is. This is the y-axis, and y equals 2 is right there. You've got to draw a line that goes through that. Specifically, this line is going to have 0 slope, so it's going to be flat. But you have to draw a line that represents y equals 2, or f of x equals 2. And so one way that I explain this is look at this as a tick mark, but think about it as a really big tick mark. Is there somebody at the door? All right, thank you. A really big tick mark, a really big tick mark. This is just a horizontal line, all right? And I'm going to go ahead and label this f of x equals 2. But again, it's linear if it has a slope, and you can see the slope right here is 0. And so that's a number. 0 is fine. 0 is a number. 0 is the slope. This is a linear function. I guess another way of looking at it is if it passes the vertical line test. Okay, does this pass the vertical line test? Yes. Does the other one? Yes, both of them do. So it's a function, but this is a linear function, meaning it's a line. So we look at the domain and the range, and again, I think about it as squashing it on the x. It's going to cover everything. Squashing it on the y, though, it's not going to cover everything. Okay, imagine if you take this thing and you've got a plate here and you've got a plate here, and you squeeze that thing together onto the y. All it's going to do is cover up a single point right there. It's only going to touch y equals 2, and that should make sense because we think about range as the y numbers, and the equation literally says y equals 2. There's no other way, there's no other number that the y could possibly be. Y equals 2. So that is not all real numbers, it's just 2. All right, so we look at the last one, x equals 5. And again, people get this backwards. People mess this up. But think about it. Here's the x-axis, and 1, 2, 3, 4, 5. Here's x equals 5 right there. All right. The line has to go through x equals 5. And a lot of times people put it the wrong way, but that doesn't make any sense. Think about it like a hash mark, okay, or a tick mark. If I made a really big tick mark, like I mean a super big tick mark, okay, this line right here is the line that represents all of the places where x equals 5. Every single point on that line has something in common. The x number is 5. That's x equals 5. All right. Now, this one, the slope, if you try to find the slope of a vertical line, the slope is undefined. This one doesn't have a slope. Okay. So that means this one is not a linear function. Imagine the vertical line test. The vertical line test is going to hit definitely more than once. It's not going to pass that vertical line test. It's not even a function. Domain. If you squash that thing down onto the x-axis, the only point that's getting covered is right there at 5. X equals 5. Well, that makes sense because that's literally what the equation says. X equals 5. That's the only x. Now the range, though, if you squash that onto the y-axis, it's going to cover up the entire y-axis. That's why in this case, the range is going to be all real numbers. Standard form of a linear equation is the same thing standard form was in Algebra 1 class. Ax plus by equals c. And we use capital letters on purpose to try and remind you of a couple of things. Over there on the right side, you've got a couple of little extra stipulations. The a number will always be positive or equal 0, I guess is what that says. Okay, positive or equal 0. Basically, the first number that you see in this equation should be positive. A, B, and C are integers. I don't want to see fractions or decimals. I would want to see integers. And the GCF of those three numbers is 1, meaning like if you had 2x plus 4y equals 6, I could reduce that. Since I could divide all three of those numbers by 2, I would. And that would reduce down, divide by 2, divide by 2, divide by 2. That's the same exact line. I just reduced that equation by a factor of 2, and that's the same exact thing. So when they say the GCF of A, B, and C is 1, basically we're trying to reduce it down to its simplest form. If A equals 0, then B is greater than 0. So they're saying if this is 0, then this better be positive. In other words, the first number you see is going to be positive. So example 2, graph the equation and give the domain and range. A lot of people are so happy with slope-intercept form, they'll change this into y equals mx plus b and graph it. You can if you want to, all right? But standard form has a second way of graphing that I think is kind of easy. If you go way back to the very first time you ever started talking about graphing, you probably made an xy table. And your teacher probably told you to plug in -2, -1, 0, 1, and 2. And you plugged in those 5 numbers and saw what came out, and you graphed those 5 points. Well, that's not very efficient. I say we only need 2 numbers, okay? We only need 2 numbers, 2 dots to see what a line looks like. And I'm going to make this as easy on myself as possible, okay? I'm going to look at an XY chart, but I'm only going to do 2 points, and I'm going to make it as easy as I can possibly do it, okay? So you might say, well, the easiest number to plug in is 0, and that's true. So I'm going to plug in 0, and I call this the cover-up method, because if you plug in a 0 for x right here, 2 times 0 is 0, that's just kind of going to go away. So I'll take my finger and like completely cover that up. And then usually I can solve the equation for y in my head. If that 2x part's gone, you've got -3y equals 12, then you probably should be able to see that y is -4 in your head. -3 times -4 equals 12. This must be -4. When x is 0, y is -4. So I've got a point. 1, 2, 3, 4. I've got the point 0, -4. All right? And I can do that really quickly in my head. Now, the next easiest number to plug into my table is not 1. Okay, it might surprise you, but the next easiest number to plug into my table is 0, but over here. Okay, so I'm trying to be lazy, and I know this is taking forever for me to explain, but once you figure this out, you can do it really quickly for standard form. So I'm plugging in 0 in for y, but that's just going to knock all of this stuff out right here, right? All that stuff's 0. So all that's going to go away. 2x plus 0 is 2x. And so I'm left with a really simple equation. I can probably solve it in my head. 2 times 6 equals 12. So I've got a second point, 6, 0, 1, 2, 3, 4, 5, 6 right there. 2 points is enough. That's enough for me to know what this line looks like. I don't have to have 5 points. 2 should be enough. So shoot your line through. And then the domain, squash it on the x. That looks like all real numbers. Range, same thing. Squash it onto the y. It's going on forever and ever. Domain and range, all real numbers. Questions? Slope formulas. The first one's going to be familiar to you. The second one, probably not. Given 2 points, m equals y2 minus y1 over x2 minus x1. You've seen that a million times. That's the slope formula. It's literally called the slope formula. But given the standard form equation, there's a different formula that you probably don't remember. M equals negative a over b. And that's a simple formula, but it's hard to remember. I don't think it's as comfortable because I've done the other one a million times. You probably haven't done that one nearly as much, maybe never. All right, so that's the way you can calculate slope if we're in standard form. So we look at example 3, find the slope, and this problem feels very familiar and very comfortable. We've got an xy point, we've got a second xy point. So we've got 2 points. We use the slope formula. y2 minus y1 over x2 minus x1. Notice you've got a minus minus there, minus negative 2. So I always like to add the opposite. Negative 6 minus 4 is negative 10. 2 plus 2 is 4. Reduce your fractions always. Reduces to negative 5 halves. That's the slope. All right. That feels like a problem you've done before. Part B, we've got 2 points. Let's do the same thing. Slope equation. y2 minus y1 over x2 minus x1. Add the opposite, that's 30. Add the opposite, negative 4 plus 4 is 0. All right, what happens when we have 0 on the bottom? That's undefined. All right, that one is undefined, and that's okay. That must mean we're talking about a vertical line. A vertical line, specifically, if you notice, the x number is negative 4. That's probably coming from the equation x equals negative 4. All right, that's a vertical line with an undefined slope. Part C is in standard form, so we've got that other equation. And so m equals negative a over b. M equals negative a over b. That's the equation. All right, now remember, for standard form, this is the a number, this is the b number, this is the c number. So really all we're doing is plugging in that capital A number, the coefficient, and that capital B number. So it's going to be the opposite of 4. And b is minus 5, so over minus 5. That means it's 4/5. And that's the slope. Now, if you're like me, you're gonna have a hard time remembering that formula. It's just an extra formula, you hardly ever see it. So you still could do what you probably your gut told you to do. If you had to find the slope of this, I bet a lot of you would say, well, let's just put it in slope-intercept form. Negative 5y equals negative 4x plus 20. Let's divide by negative 5. And so y equals 4/5 x minus 4. There's your slope right there, right? And so I think that probably feels a lot more comfortable to you than memorizing an extra formula. But if you think about it, that formula is doing really what we did. All right. It's just taking the extra stuff out that we didn't need. In order to find the slope, we subtracted this thing over and we divided by this thing. That's what the formula says. Average rate of change describes how much a quantity changes. A positive value indicates an increase and a negative value indicates a decrease. It's an application of the slope formula. Basically, we're talking about slope. All right. When they say rate of change, they're talking about slope. Find the average rate of change, find the slope. That's what they're saying. So this complicated looking problem number 4 is basically going to be a slope problem. In 2010, the government spent that much money on research. In 2013, the government spent that amount of money on research. Find the average rate of change in the amount of money spent on research. Graph the data as a line segment and interpret the result. All right, so I think the hardest thing about this is graphing those nasty looking numbers, but we got this. All right, I'm gonna break the scale, and I'm gonna start right here, and let's call that 2010. Okay, so I skipped 2 tick marks, 2010. I'm gonna skip 2 tick marks and call that 2011. Skip 2 and call that 2012. Skip 2 and call that 2013. Time is almost always going to be on your x-axis, but there's time. Now the other number, the amount of money, that's a weird amount of money to think about, 9,000 million. So we're probably going to have the scale be in the millions. So what I'm going to do is I'm going to go up 1, 2, 3, 4, 5 right here, and I'm going to call that 5,000 million. And then 6, 7, 8, 9, 10. That's going to be $10,000 million. Is that weird? That's kind of a weird thing to say, but $10,000 million because it's in millions. All right. So mainly we're just graphing a point, and the first sentence gives us the first point. X is the time, and Y is that amount of money. So we've got 9,547 million. So at 2010, I'm going to go up to about right here. It's basically 9.5 on a 10-point scale. Okay, that would be where $9,547 million is. And so then in 2013, that's your second X point, and 8658 is your second Y point. So we go to 2013 and about 8.6 on a 10-point scale. So there's 8.6 about right there, right? So they want me to graph the data as a line segment. And first thing was find the average rate of change. So find the average rate of change is the slope. Okay, so average rate of change equals, right? So it's just the slope formula, y2 minus y1 over x2 minus x1. So this is my y2 and this is my y1. 8,658 minus 9,547 And then 2013 was my x2, and 2010 was my x1. So 2013 minus 2010. So subtracting, you're probably going to want a calculator for this. All right. I've already done this ahead of time. So if I subtract those numerators, 86, 58 minus 95, 47, I get negative 889. On the bottom, 2013 minus 2010 is 3. And so there's my slope. But that's kind of a hard number to understand. So I would go ahead and type that in on the calculator. Negative 889 divided by 3 gives me approximately negative 296.3. That's my average rate of change. Let's box it just to be consistent. So find the average rate of change. There it is. Graph the data as a line segment. Got it. And interpret the result. Well, remember up above it said negative value indicates decrease. That's what's happening. We've got a negative value, so it's decreasing. But that's what the line shows. The line shows it's decreasing as well. So let's just say the amount spent is decreasing by an average of 296.3 million each year.